let yourself settle in just for a moment. Find that place where your body naturally wants to rest, where the weight of the day can finally begin to lift from your shoulders, like morning mist rising from a quiet lake. Take a slow, deep breath, feeling the cool air move through you, and as you exhale, let any lingering tension dissolve into the space around you, dispersing like smoke in a gentle breeze. Tonight, we're embarking on a journey through the cosmos. But this isn't a journey that requires anything of you except your willingness to drift alongside the story. Close your eyes if you'd like, or let them rest softly on some distant point, unfocused and calm. Allow the words to wash over you like waves lapping at a shore, painting pictures in your mind of distant worlds and cosmic possibilities that stretch far beyond our everyday experience. We're going to explore something profound, something that touches the very heart of what it means to be human, looking up at the stars. We're going to talk about the search for another Earth, a world perhaps not so different from our own, orbiting a distant star in the vast darkness of space. But more than that, we're going to explore what it might mean if that world is already occupied, if life has found a way to flourish there, just as it has here, on our pale blue home. This is a story about discovery, about the incredible tools we built to peer across unimaginable distances, and about the ancient human impulse to wonder if we're alone. So breathe, relax, and let's drift together into the depths of space, where the most revolutionary telescope ever built is revealing secrets that could change everything we think we know about life in the universe. Before we begin this cosmic journey, if you find yourself enjoying these explorations of science and space, these gentle dives into the mysteries of the universe, please consider subscribing to The Science Pillow. Your support helps us continue creating these calming educational experiences, and hitting that like button lets us know you're finding value in these nighttime voyages through the cosmos. Now, let's begin our story. The night sky and our ancient question. Look up on a clear night, away from the glare of city lights, and you'll see what every human being who has ever lived has seen. Thousands upon thousands of points of light scattered across the darkness, like diamonds on black velvet. For most of human history, those points of light were mysteries wrapped in wonder. Ancient peoples wove them into stories, connected them into constellations that helped them navigate across deserts and oceans, used them to mark the passage of seasons and years. The ancient Greeks looked at those lights and wondered. Philosophers like Epicurus, writing in the 3rd century before the Common Era, proposed that the universe must contain an infinite number of worlds. It seemed only logical to him that if atoms could combine to create our world, they could combine elsewhere to create others. His contemporary Metrodorus of Chios put it simply: to consider the Earth the only populated world in infinite space is as absurd as to assert that in an entire field sown with millet, only one grain will grow. But these were philosophical musings, beautiful thoughts, without any way to test them. For thousands of years, we had no way to know if those points of light in the sky were anything like our sun, much less if they hosted worlds of their own. We wondered, we speculated, we wrote stories about travelers to other worlds, but we had no way to know. The scientific revolution changed everything. When Nicolaus Copernicus proposed, in 1543, that the Earth orbited the Sun rather than the Sun orbiting the Earth, it was more than just a rearrangement of the solar system. It was a fundamental shift in how we understood our place in the universe. If the Earth wasn't the center of everything, if it was just another planet orbiting the Sun, then perhaps our Sun was just another star, and perhaps other stars had their own planets. Giordano Bruno, an Italian philosopher and mathematician, took this idea and ran with it. In the late 1500s, he proposed that the stars were distant suns, each surrounded by their own worlds, some of which might harbor life. It was a radical idea, one that contributed to his eventual execution by the Roman Inquisition in the year 1600. But the idea didn't die with him. It lived on, waiting for the technology that could prove it true. Galilei turned his telescope to the heavens in 1609, and what he saw revolutionized our understanding of the universe. He saw mountains on the moon, proving it was a world like Earth, not a perfect sphere of heavenly light. He saw 4 moons orbiting Jupiter, proving that not everything in the universe orbited the Earth. He saw that the Milky Way, that band of light across the night sky, was made of countless individual stars. Each discovery chipped away at the idea that Earth and humanity were unique in all creation. But actually, detecting planets around other stars would prove almost impossibly difficult. These worlds, if they existed, would be incredibly far away, tiny compared to their parent stars, and lost in the overwhelming glare of starlight. Imagine trying to spot a firefly next to a searchlight from hundreds of miles away, and you begin to understand the challenge. The first serious attempts to detect exoplanets didn't come until the 20th century. Astronomers knew that a planet orbiting a star would cause that star to wobble slightly, pulled back and forth by the planet's gravity. If you could measure that wobble with enough precision, you could infer the presence of a planet. But the wobble was so tiny, the measurements so difficult, that false alarms were common. Claims of exoplanet discoveries came and went, unable to be confirmed. Then, in 1995, everything changed. Swiss astronomers Michel Mayer and Didier Queloz announced the discovery of 51 Pegasi b, the first confirmed planet orbiting a sun-like star. It was a strange world. A gas giant larger than Jupiter, but orbiting its star closer than Mercury orbits our sun, completing an orbit in just over 4 days. It was nothing like anything in our solar system, and it opened scientists' eyes to the incredible diversity of planetary systems that might exist. The floodgates opened. New detection methods were developed and refined. The radial velocity method that found 51 Pegasi b was joined by the transit method, which looked for the tiny dip in a star's light when a planet passed in front of it. Space telescopes like Kepler and TESS were launched, staring at thousands of stars simultaneously, watching for those telltale dips in brightness. The numbers are staggering. We now know of more than 6,000 confirmed exoplanets, with thousands more candidates awaiting confirmation. We've found massive gas giants orbiting closer to their stars than Mercury orbits the Sun, their atmospheres heated to thousands of degrees. We've found ice giants in the outer reaches of distant solar systems. We found planets orbiting not 1, but 2 stars. Worlds where you'd see a double sunset, like the one Luke Skywalker saw on Tatooine. We've found rogue planets drifting through interstellar space, untethered to any star. And crucially, we've found rocky planets, worlds made of metal and stone, like Earth, Mars, Venus, and Mercury. Some are larger than Earth, so-called super-Earths. Some are smaller. Some orbit close to their stars, baked to temperatures where lead would melt. Others orbit far away, frozen and dark. And some, tantalizingly, orbit in that special zone around their stars where temperatures might be just right for liquid water to exist on their surfaces. This zone, called the habitable zone, or sometimes the Goldilocks zone, is neither too hot nor too cold. It's the region where a rocky planet with the right atmosphere might maintain liquid water on its surface. And where there's liquid water, there might be life, at least life as we understand it. Every major star-forming region we've studied shows signs of planet formation. Planets, we now know, aren't rare. They're abundant, scattered throughout our galaxy like grains of sand on a beach. Statistical analyses suggest there could be billions of Earth-sized planets in the habitable zones of sun-like stars in our galaxy alone. Billions of worlds where the conditions might be right for life. The question that ancient philosophers could only ponder, that question of whether we're alone in the universe, has transformed from philosophical speculation to a scientific investigation that's happening right now, in our lifetime. But knowing that these planets exist and actually studying them are two very different things. Most exoplanets we've detected are known to us only through their effects on their parent stars. We see the wobble they cause, or the dimming of starlight as they pass in front of their stars. But we don't actually see the planets themselves. We know they're there, we know roughly how big they are and where they orbit, but we know almost nothing about what they're actually like. Do they have atmospheres? If so, what are those atmospheres made of? Do they have water? Do they have continents and oceans? Are there seasons, weather, storms? And most tantalizing of all, is there any sign, any hint at all, that these distant worlds might host life? To answer those questions, we needed a telescope unlike any that had come before. We needed an instrument so sensitive, so powerful, that it could analyze the atmospheres of planets orbiting other stars, detecting the chemical fingerprints of gases that might hint at conditions suitable for life, or even at life itself. The James Webb Space Telescope, humanity's new eyes. The James Webb Space Telescope is, without exaggeration, one of the most remarkable machines humanity has ever built. It represents decades of work, billions of dollars of investment, the collaboration of thousands of scientists and engineers across multiple countries, and technological innovations that pushed the boundaries of what was thought possible. And on Christmas Day, 2021, it left Earth aboard an Ariane 5 rocket, beginning a journey that would take it nearly 1 million miles from home. To understand what makes Webb so special, we need to understand what it's designed to do. The telescope's primary mission is to look back in time, to see the first galaxies that formed after the Big Bang, to watch stars and planetary systems being born, and yes, to study the atmospheres of exoplanets. But unlike its famous predecessor, the Hubble Space Telescope, which observes primarily in visible light, Webb observes in infrared. Infrared is light with wavelengths longer than what our eyes can see. It's the kind of light that warm objects emit, the heat radiation you feel from a campfire or a hot stove, and it has a special property that makes it perfect for studying the early universe and distant planets. It can pass through dust and gas that would block visible light. More importantly for exoplanet science, when you observe a star and its planet in infrared, the contrast between them is much better than in visible light. The star is still brighter, but not as overwhelmingly so, making it easier to study the planet. Webb's mirror is massive, 6.5 meters across, made up of 18 hexagonal segments that work together as one. It's covered in a microscopically thin layer of gold, which reflects infrared light exceptionally well. That mirror collects light from the cosmos and focuses it onto 4 main scientific instruments, each designed to study the universe in different ways. For exoplanet science, the most important instruments are NIR SPEC, the near-infrared spectrograph, and MIRI, the mid-infrared instrument. These spectrographs work by splitting light into its component wavelengths, like a prism splitting white light into a rainbow. Different chemicals absorb light at specific wavelengths, leaving dark lines or bands in the spectrum. By studying which wavelengths are missing, scientists can determine what chemicals are present. It's like chemical fingerprinting from millions or billions of miles away. But there's a catch. To observe in infrared, the telescope itself must be incredibly cold. If it were warm, it would emit its own infrared light, drowning out the faint signals from distant objects. This is why Webb is positioned nearly 1,000,000 miles from Earth at a special point called the second Lagrange point, or L2. At this location, the telescope can keep the Sun, Earth, and Moon all on one side, shielded by a massive sun shield the size of a tennis court. That sun shield is an engineering marvel in itself. It's made of 5 layers of material called capton, each layer thinner than a human hair, separated by gaps to maximize insulation. The sunward side faces temperatures around 80 to 5 degrees Celsius, hot enough to boil water. The side facing deep space, where the telescope's instruments sit, stays at about minus 233 degrees Celsius, just a few degrees above absolute zero. This temperature difference, maintained across just a few meters, is what allows Webb to see the faintest infrared glows from across the universe. The journey to L2 took about a month, but it was one of the most nerve-wracking periods in the history of space exploration. Webb couldn't fit fully assembled inside any rocket, so it had to launch folded up, like cosmic origami, then unfold itself in space. Over 344 single points of failure had been identified, 344 things that, if they went wrong, could cripple or destroy the mission. Engineers had tested and retested every mechanism, every motor, every deployment sequence. But once Webb left Earth, there was no sending astronauts to fix problems like we did with Hubble. It was billions of miles away, operating autonomously, unfolding in a carefully choreographed sequence of deployments. The sun shield deployed first, layer by layer, each one unfolding and separating. Then, the secondary mirror, mounted on a boom, swung into position. Finally, the primary mirror's wing segments, which had been folded back for launch, rotated outward and locked into place. Each deployment was a moment of held breath for everyone watching. And, miraculously, beautifully, everything worked perfectly. But the mirror deployment was just the beginning. Each of the 18 mirror segments had to be aligned with incredible precision, working together to focus light as if they were a single, perfect mirror. Using tiny motors that could adjust each segment by nanometers, engineers spent months aligning the mirror, a process that required more than 1,000 different adjustments. They directed the telescope to look at a single bright star and slowly adjusted each segment until all 18 images of that star merged into one perfect point of light. The first images from Webb, released in July 2002, took the world's breath away. Deep fields showing thousands of galaxies, each one containing billions of stars. Star-forming nebulae revealed in unprecedented detail, showing the birth of new solar systems. Dying stars surrounded by shells of gas, the elements they forged in their cores now drifting out to seed the next generation of stars and planets. But for those interested in the search for life beyond Earth, the most exciting early results were the exoplanet observations. Webb can observe exoplanets in several ways. For planets that transit in front of their stars, Webb can watch starlight filtering through the planet's atmosphere during the transit. Different chemicals in that atmosphere absorb light at specific wavelengths, leaving their fingerprints in the spectrum. For planets that don't transit but are far enough from their stars, Webb can sometimes observe them directly, analyzing the light they reflect or the heat they emit. Early observations targeted hot gas giants, worlds easier to observe because they're larger and often have extended, puffy atmospheres. Webb detected water vapor, carbon dioxide, methane, and even signs of clouds and weather systems. On WASP-39b, a gas giant larger than Saturn, Webb detected sulfur dioxide, a chemical that forms when sunlight breaks down other sulfur-bearing molecules, providing direct evidence of photochemistry happening in an alien atmosphere. But the holy grail of exoplanet science isn't studying hot gas giants. It's studying rocky, Earth-sized planets in the habitable zones of their stars, worlds where liquid water could exist, where life might have taken hold. These worlds are much harder to observe. They're smaller, so the signals are fainter. Their atmospheres, if they have them, are thinner and less extended. But Webb is powerful enough, sensitive enough, that for the first time in human history, we can attempt it. And what Webb has found, what it's still finding as observations continue, is reshaping our understanding of what's possible on worlds beyond our own. The telescope has revealed rocky planets that might have atmospheres, detected chemicals that hint at processes we associate with life, and identified worlds that challenge our assumptions about where and how life might exist. In particular, Webb has turned its powerful gaze towards several systems that offer our best chances yet of finding signs of life beyond Earth. The hunt for Earth-like worlds. To understand what makes a planet Earth-like, we need to think about what makes Earth special. What combination of factors has allowed our world to harbor life for billions of years? It's not just about size, though, that matters. It's not just about being rocky rather than gaseous, though that's important too. It's about a complex interplay of factors, each contributing to Earth's habitability. Size matters because it determines gravity, which affects whether a planet can hold on to an atmosphere. Too small, like Mars, and atmospheric gases can escape into space over time. Too large, and the planet might attract and retain vast amounts of hydrogen and helium from the surrounding nebula during formation, becoming more like Neptune than Earth. Earth-sized generally means somewhere between half and twice Earth's mass, a range where rocky composition and atmosphere retention are both likely. Being rocky, made primarily of silicates and metals rather than gas, is crucial because rocky planets have solid surfaces where complex chemistry can occur, where oceans can gather, where continents can rise. The composition of Earth's core and mantle drives plate tectonics, the movement of crustal plates that recycles carbon, regulates climate over geological time, and may be essential for long-term habitability. Temperature is obviously critical, and that's where the habitable zone concept comes in. The habitable zone is the region around a star where a rocky planet could, in principle, maintain liquid water on its surface. Too close to the star, and water boils away into space. Too far, and it freezes solid. The exact boundaries of this zone depend on the star's temperature and brightness. And they're not fixed lines, but rather fuzzy regions of probability. For a star like our Sun, the habitable zone extends from about 0.95 to 1.37 astronomical units, where 1 AU is the distance from Earth to the Sun. Earth sits comfortably within this zone at 1 AU. Venus at 0.72 AU is too close, suffering a runaway greenhouse effect that has given its surface temperatures hot enough to melt lead. Mars, at 1.52 AU, is just beyond the outer edge, though it might have been wetter and warmer in its distant past. But the habitable zone is just a starting point, a first-order approximation. Being in the habitable zone doesn't guarantee habitability. You need the right atmosphere, the right atmospheric pressure. Venus is technically in some definitions of the Sun's habitable zone, but its crushing carbon dioxide atmosphere creates such an intense greenhouse effect that the surface is utterly inhospitable. Mars, conversely, has so little atmosphere that liquid water can't remain stable on its surface for long. The right kind of star matters too. Our Sun is a G-type main sequence star, relatively stable, not too hot, not too cool, with a lifespan of about 10 billion years. Stars much more massive than the Sun burn brighter, but live shorter lives, perhaps not giving planets enough time for life to evolve. Stars much smaller than the Sun, the red dwarfs that make up about 70% of all stars, can live for trillions of years, but they present their own challenges. Red dwarfs are cooler and dimmer than the Sun, which means their habitable zones are much closer in. A planet in a red dwarf's habitable zone might orbit its star every few days to few weeks, not a year. At such close distances, tidal forces from the star would likely lock the planet's rotation, so one side always faces the star in eternal day, while the other faces away in eternal night. This could create extreme temperature differences unless the planet has an atmosphere thick enough to circulate heat from the day side to the night side. Red dwarfs also tend to be more active than the Sun, especially when they're young, producing powerful flares and stellar winds that could strip away planetary atmospheres. A planet in a red dwarf's habitable zone would be bathed in higher levels of ultraviolet and X-ray radiation than Earth receives, potentially sterilizing the surface, or at least making life much more challenging. Yet red dwarfs can't be ignored. They're so common and they live so long that if planets around them can be habitable, the number of potentially life-bearing worlds in the galaxy could be enormous. This is why so much attention has focused on finding and studying rocky planets in red dwarf habitable zones. They're our most abundant opportunity to find life, if it can exist there. Detecting these Earth-like worlds is an incredible technical challenge. The first method that found them was the radial velocity method, watching for the tiny wobble a planet induces in its star as they orbit their common center of mass. It works well for finding larger planets, but Earth mass planets induce such small wobbles that they're at the limits of detection even with the best instruments. The transit method has proven more effective for finding small planets. When a planet passes in front of its star from our perspective, it blocks a tiny fraction of the star's light. For an Earth-sized planet transiting a Sun-like star, the dimming is about 0.0084%, less than 1 part in 10,000. Detecting that requires incredibly precise measurements of stellar brightness. But space telescopes like Kepler and TESS were designed specifically for this task. Kepler, launched in 2009, stared at a single patch of sky containing about 150,000 stars, measuring their brightness every 30 minutes for over 4 years. It found more than 2,700 confirmed planets, including many Earth-sized worlds and worlds in habitable zones. TESS, launched in 2018, surveys the entire sky, finding planets around the brightest nearby stars, making them ideal for follow-up studies with telescopes like Webb. Direct imaging, actually photographing a planet separate from its star, is still incredibly difficult for Earth-sized worlds. It's possible for large planets far from their stars, where the contrast is better and the angular separation is larger. But for an Earth analog around a Sun-like star, we don't yet have the technology. Future telescopes, like NASA's proposed Habitable Worlds Observatory, are being designed specifically to directly image and study Earth-like exoplanets. So where do we stand in the search for Earth's twins? We know they exist. Kepler's data suggests that roughly 20 to 50% of Sun-like stars have rocky planets in their habitable zones. With hundreds of billions of stars in our galaxy, that translates to tens of billions of potentially habitable worlds. We've identified hundreds of candidates, worlds that are roughly Earth-sized and orbit in their star's habitable zones. But knowing a planet exists and understanding whether it's actually habitable are very different questions. We need to know if these worlds have atmospheres. We need to know what those atmospheres are made of. We need to look for chemicals that might indicate habitable conditions, or better yet, biosignatures, chemicals that might indicate the presence of life. This is where Webb comes in. For the first time, we have a telescope powerful enough to begin answering these questions. We can observe planets as they transit their stars, analyzing the starlight filtering through their atmospheres. We can observe them as they pass behind their stars, measuring the infrared heat they emit. We can begin, tentatively, to characterize these distant worlds and search for signs that they might host life. Several systems have emerged as prime targets for this search, worlds where Webb's observations are peeling back the mysteries, revealing what conditions might be like on planets that could be Earth's distant cousins. Let's explore some of these worlds, starting with a remarkable system of 7 Earth-sized planets orbiting a small red dwarf just 40 light-years away. TRAPPIST-1, a system of Earths, about 40 light-years from Earth, in the constellation Aquarius. There's a star so small and dim that despite its relative closeness, you can't see it without a telescope. This star, officially designated 2MSS J23262928050, 2285, but better known as TRAPPIST-1, is a red dwarf with only about 9% the mass of our Sun. It's so cool and dim that if you could somehow stand on the surface of one of its planets, it would appear distinctly red, bathing the landscape in crimson light. In 2017, astronomers made an announcement that captured imaginations around the world. TRAPPIST-1 wasn't just orbited by 1 or 2 planets, as many stars are. It hosted 7 rocky planets, all of them roughly Earth-sized, all of them packed into orbits closer to their star than Mercury is to our Sun. It was, and remains, the system with the most Earth-sized planets ever discovered around a single star, a miniature planetary system that could fit entirely within the orbit of our innermost planet. The system was first discovered using a network of ground-based telescopes called TRAPPIST, the TAND Planets, and Planetes EMAL's Small Telescope. Project astronomers watched as the star's brightness dipped periodically, indicating planets passing in front of it. Follow-up observations with NASA's Spitzer Space Telescope and other observatories revealed the full 7-planet system, and additional studies refined our understanding of these worlds. Let's journey through this system, starting closest to the star and moving outward. TRAPPIST. 1b, the innermost planet, orbits its star every 1.5 days. It receives about 4 times the radiation that Earth gets from the Sun, making it far too hot for liquid water. With a mass about 1.4 times Earth's and a size slightly larger, it's definitely rocky, but probably baked dry and airless. TRAPPIST-1c orbits every 2.4 days and receives about twice Earth's radiation. It's also too hot for habitability, as we understand it, though intriguingly, early observations suggested it might have a carbon dioxide atmosphere. Later observations with Webb, however, found no evidence of a thick atmosphere, suggesting that if there is one, it must be very thin, or composed of heavier molecules. Then we reach TRAP, PIST, 1D, orbiting every 4.05 days at the inner edge of what many scientists consider the habitable zone. It receives about the same amount of radiation as Venus does from our Sun, which puts it right on that border between too hot and potentially just right. Webb observations of TRAP, PIST, 1D in 2025 found no evidence of an Earth-like atmosphere rich in water, methane, or carbon dioxide. The planet appears to lack the kind of thick, familiar atmosphere we might have hoped for. But the absence of an Earth-like atmosphere doesn't necessarily mean no atmosphere at all. TRAP-PIST, one could have a different type of atmosphere, perhaps dominated by carbon dioxide like Venus or Mars or something else entirely. More observations are planned to probe this possibility. The planet's position at the edge of the habitable zone makes it a crucial test case for understanding how habitability varies across different stellar environments. TRAP, PIST, 1E, the fourth planet, is where things get really interesting. Orbiting every 6.1 days, it sits comfortably in the middle of the habitable zone. It's slightly smaller than Earth and less massive, but by far the most Earth-like in terms of its density and the amount of radiation it receives. If any planet in the system is going to have liquid water on its surface, this one seems like the best bet. Webb has observed TRAP, PIST, 1E multiple times, and the results are complicated. Early observations in 2025 found hints that might be consistent with methane in the planet's atmosphere, a potential biosignature. But the signals are subtle, and they might also be explained by activity in the star itself. Red dwarfs like TRAP, PIST, one can have complex atmospheres with molecules like methane, and separating the planet's signal from the stars is a significant challenge. Follow-up observations are attempting to address this by observing the planet during what's called a dual transit, when both TRAP, PIST, 1E and TRAP, PIST, 1B, the innermost planet known to be airless, pass in front of the star at the same time. By comparing the signals, astronomers hope to separate what's coming from the star from what's coming from the planet's atmosphere. As of now, the jury is still out on whether TRAP, PIST, 1E has an atmosphere, but it remains one of the most compelling habitable zone planets for further study. TRAP, PIST, 1F, the fifth planet, orbits every 9.2 days and also lies in the habitable zone, though toward the colder outer edge. It receives about 37% of Earth's radiation, placing it in a position similar to Mars in our solar system. But unlike Mars, TRAP, PIST, 1F is more massive and larger, meaning it could potentially hold on to a thicker atmosphere. If it has a substantial greenhouse atmosphere, it might warm itself enough to maintain liquid water. TRAP, PIST, 1G, the sixth planet, orbits every 12.4 days at the outer edge of the habitable zone. It receives only about 23% of Earth's radiation, making it quite cold unless it has a very thick atmosphere, creating a strong greenhouse effect. Little is known about this planet's atmosphere so far, but it remains a target for future observations. Finally, TRAP, PIST, 1H, The outermost known planet orbits every 18 to 20 days, well beyond the habitable zone. It receives only about 13% of Earth's radiation and is almost certainly frozen solid unless some internal heat source, perhaps tidal heating from gravitational interactions with the other planets, warms it from within. Intriguingly, there's a possible eighth planet tentatively detected in 2025 that would orbit even further out, though its existence hasn't been confirmed. What makes TRAPPIST so special isn't just that it has 7 roughly Earth-sized planets, though that's remarkable enough. It's that 3, possibly 4 of these planets orbit in or near the habitable zone. It's that the entire system is close enough and compact enough that we can study these planets in detail with Webb. And it's that studying this system teaches us about how planets around red dwarfs behave, which is crucial because red dwarfs are the most common type of star in the galaxy. The TRAPPIST, one planets face challenges that Earth doesn't. They're almost certainly tidally locked, with one side permanently facing the star and the other in perpetual darkness. The star flares regularly, bombarding the planets with high-energy radiation. The planets are packed so closely together that you could see neighboring worlds in the sky, appearing several times larger than the Moon appears from Earth. A stunning vista that underscores how different this system is from our own. Yet despite these challenges, the possibility remains that one or more of these worlds could be habitable. Perhaps thick atmospheres circulate heat from the day side to the night side, moderating temperature extremes. Perhaps the planets have magnetic fields strong enough to shield them from stellar radiation. Perhaps life, if it exists, has adapted to conditions we wouldn't consider hospitable. Webb's observations of TRAPPIST-1 are ongoing, with more time allocated to study these worlds in greater detail. Each observation reveals more about these planets, constraining what kinds of atmospheres they might have, building a more complete picture of what conditions are like in this alien solar system. The TRAPPIST-1 system represents our best laboratory for studying whether Earth-sized planets around red dwarfs can be habitable, a question with profound implications given how common such stars are. But while TRAPPIST-1 offers multiple potentially habitable worlds to study, there's another planet orbiting a different type of star where Webb has made perhaps the most tantalizing discovery yet. A detection that has sent ripples of excitement through the scientific community and beyond. K2-18b and the Biosignature hint. 124 light-years from Earth, in the constellation Leo, there's a red dwarf star called K2-18. It's slightly cooler and smaller than our Sun, though larger and warmer than TRAPPIST-1. And orbiting this star, right in the middle of the habitable zone, is a planet that has become one of the most fascinating objects in the entire search for extraterrestrial life. K2-18b was discovered in 2015 by NASA's Kepler Space Telescope, one of hundreds of planets the mission found. At first, it didn't seem particularly special. It's a sub-Neptune, a type of planet we don't have in our solar system. Bigger than Earth, but smaller than Neptune. With about 8.6 times Earth's mass and a radius about 2.6 times larger, it sits in that intermediate category that's so common in the galaxy, but so poorly understood. For a while, K2-18b was just another entry in the exoplanet catalog. But in 2019, observations with the Hubble Space Telescope revealed something extraordinary. Water vapor in the planet's atmosphere. It was the first time water vapor had been detected in the atmosphere of a planet in the habitable zone, and it immediately elevated K2-18b's status as a target for further study. The presence of water vapor raised a fascinating possibility. Maybe K2-18b wasn't a mini Neptune, a smaller version of our ice giants with no solid surface and a thick hydrogen envelope. Maybe it was what scientists call a Hycean world, a new class of potentially habitable planet that was only beginning to be theoretically explored. A Hycean planet, short for hydrogen ocean, would have a liquid water ocean beneath a hydrogen-rich atmosphere. It's a configuration we don't see in our solar system, but that might be common elsewhere. Such a planet would be larger than Earth, with stronger gravity and a thicker atmosphere, but underneath all that hydrogen and helium, there could be a global ocean kilometers or even hundreds of kilometers deep. And where there's liquid water, there might be life. The concept is exciting because if Hycean worlds can be habitable, it dramatically expands the number of potentially life-bearing planets. Sub-Neptunes are the most common type of exoplanet we found, far more common than Earth-sized rocky worlds. If even a fraction of them turn out to be ocean worlds beneath hydrogen atmospheres, the galaxy could be teeming with habitable environments we never imagined. In 2023, the James Webb Space Telescope turned its powerful instruments toward K2-18b, and what it found sent shockwaves through the scientific community. Webb's observations confirmed the presence of methane and carbon dioxide in the planet's atmosphere, both carbon-bearing molecules. This alone was significant, the first time such molecules had been detected on an exoplanet in the habitable zone, using Webb's unprecedented precision. But there was more. Buried in the spectral data was a tentative signal, a hint of something that made astronomers sit up and take notice. The signal was consistent with the presence of dimethyl sulfide, or DMS, and possibly dimethyl disulfide, DMDS. On Earth, these molecules are produced almost exclusively by biological activity, particularly by marine phytoplankton, the microscopic organisms that form the base of oceanic food chains. Let that sink in for a moment. Here was a planet orbiting another star 124 light-years away, and Webb had detected a chemical that in all our study of Earth's atmosphere and biosphere, we found is created almost entirely by life. It was, potentially, a biosignature, a chemical fingerprint of biological activity on another world. The detection was initially at what statisticians call the 3 sigma level, meaning there was about a 0.3% probability that the signal arose by random chance or measurement error. That's significant, but it's not definitive. In science, particularly for extraordinary claims, we require 5 sigma significance, meaning less than a 0.00006% probability of a false positive before we claim a discovery. 5 sigma is the threshold that was used to announce the detection of the Higgs boson. It's the standard for "we're really, really sure." The team behind the discovery, led by Professor Nikku Madhusudan at the University of Cambridge, was appropriately cautious. They emphasized that, while the detection of DMS or DMDS was the strongest biosignature candidate to date, it remained tentative. There could be unknown abiotic processes, chemical reactions that don't involve life, that could produce these molecules on a planet so different from Earth. On Earth, DM's concentrations in the atmosphere are typically below 1 part per billion by volume. On K2-18b, if the signal is real, the concentration would be thousands of times higher, over 10 parts per million. That's a massive difference, and it raises questions. Why would biological processes produce so much more DMs on K2 18b than on Earth? Or is there some non-biological chemistry at work that we don't understand? Follow-up observations were proposed and approved. In 2025, Webb observed K2 18b again, this time using a different instrument, MIRI, the mid-infrared instrument. The goal was to confirm or refute the DM signal. The spectral features of DMS and DMDS overlap in some wavelengths but differ in others, so more observations across a wider range of wavelengths could help differentiate between the two molecules and increase confidence in the detection. The latest results, published in 2025, strengthened the case. The signal remained consistent across multiple observations and different instruments. The statistical significance had improved, though it still hadn't quite reached the gold standard 5 sigma threshold. The team estimated that another 16 to 24 hours of observation time with Webb could push the detection to 5 sigma, definitively confirming or ruling out the presence of these molecules. But even if the DM signal is confirmed at 5 sigma, that doesn't necessarily mean life. Scientists like Eddie Schwieterman at the University of California, Riverside, who studies biosignatures, pointed out some puzzles. If DMs or DMDS were present at the detected levels, you'd expect to see other molecules as well, byproducts of the ultraviolet radiation from the star, breaking down these sulfur compounds. Specifically, you'd expect to see ethane, a simple hydrocarbon that should form when DMS breaks down. But Webb hasn't detected ethane on K2 18b, at least not yet. This could mean several things. Maybe the atmospheric models are incomplete, missing some chemistry that prevents ethane from forming or removes it as fast as it's created. Maybe there's some aspect of K2 18b's atmosphere we don't understand, some circulation pattern or temperature structure that's different from expectations. Or maybe the DMS signal isn't as strong as it appears, or isn't DMS at all but some other molecule with similar spectral features. Sarah Seeger at MIT, another leading voice in exoplanet science, has expressed both excitement and caution. The methodology is sound, the observations are high quality, but the interpretation remains challenging. We're dealing with a highly averaged signal from an enormously complex three-dimensional atmospheric system, trying to deduce the presence of specific molecules at specific concentrations. It's an incredibly difficult task, and parallel interpretations of the data will exist until we have more observations or a more comprehensive understanding of how such planets work. The broader context of K2 18b's atmosphere provides some constraints. The presence of methane and carbon dioxide, both confirmed, is interesting in itself. Methane can be produced by geological processes or by life. On Earth, the vast majority of atmospheric methane comes from biological sources, both from microbes and from larger organisms. But methane can also be produced by volcanic activity or by chemical reactions in the presence of water and certain minerals. Carbon dioxide is even more ambiguous. It's produced by volcanoes, by the weathering of rocks, by the metabolism of almost all living things. Its presence tells us that carbon is cycling through K2 18b's system, but it doesn't tell us whether life is involved. What makes the DM's detection so compelling, if real, is that we don't know of any non-biological processes that produce it in significant quantities. That's what makes it such a strong biosignature candidate. But we don't know of any is different from there aren't any. K2 18b is not Earth. It's a world perhaps 4 times larger in radius, with gravity about twice as strong, with an atmosphere that might be primarily hydrogen, orbiting a star quite different from our Sun. The chemistry happening there could be unlike anything we see on Earth or can easily simulate in laboratories. This is the fundamental challenge of biosignature detection. We need to understand not just whether a molecule could be produced by life, but whether it could be produced by anything else, and whether the environment of the planet is conducive to whichever process is creating it. It requires understanding planetary geology, atmospheric chemistry, stellar radiation, and more. All for a world we can never visit, that we can only study through the tiny fraction of starlight that filters through its atmosphere. Despite the uncertainties, K2-18b represents a watershed moment in the search for life beyond Earth. For the first time, we have a realistic biosignature candidate on a planet in the habitable zone. Even if it turns out that the DM signal is produced by some exotic but non-biological chemistry, the fact that we can detect such molecules at all is revolutionary. We're doing chemistry on another world, analyzing its atmosphere molecule by molecule, searching for signs that might indicate life. The observations of K2-18b will continue. More time with Webb has been allocated. Other telescopes will join the effort, and in the 2030s and 2040s, the next generation of telescopes like the Extremely Large Telescope in Chile and NASA's Habitable Worlds Observatory will have even greater capabilities. Perhaps they'll definitively answer whether K2-18b hosts life, or perhaps they'll reveal even more tantalizing mysteries. But while K2-18b is the most exciting biosignature candidate at 124 light-years away, there's another world much closer to home that offers a different kind of promise in the search for inhabited worlds. Proxima Centauri b, our nearest neighbor. If you want to think about visiting another potentially habitable planet, if you want to imagine humanity one day sending probes or even people to another world that might host life, there's one obvious first choice: Proxima Centauri b, the closest known exoplanet in a star's habitable zone. Proxima Centauri, the closest star to our Sun, sits just 4.2 light-years away in the constellation Centaurus. It's part of a triple star system, with Alpha Centauri A and B, those two bright stars that form a binary pair visible from the southern hemisphere. Proxima is the third member of this system, a red dwarf so faint that despite being our nearest stellar neighbor, you need a telescope to see it at all. In 2016, an international team of astronomers, led by Guillaume Anglada-Escudé at Queen Mary University of London, announced the discovery of Proxima Centauri b. They'd been conducting an intensive observation campaign called the Pale Red Dot Project, a reference to Carl Sagan's famous description of Earth as a pale blue dot. For this red dwarf star, any planet it hosted would be bathed in pale red light. The discovery was made using the radial velocity method, watching for the tiny wobble in the star's motion caused by the planet's gravity. The signal was subtle, requiring careful measurements over months to distinguish it from the star's natural variability and activity. But eventually, the pattern emerged: a planet with a minimum mass of about 1.17 times Earth's mass, orbiting the star every 11.2 days. Every 11.2 days. That's how long a year lasts on Proxima Centauri b. The planet orbits its star at a distance of just 0.0485 astronomical units, about 5% of the distance from Earth to the Sun. If you could somehow transplant Proxima b into our solar system at that distance, it would be orbiting well inside Mercury's orbit, far too close to our Sun to be anything but a charred cinder. But Proxima Centauri isn't our Sun. It's a red dwarf, cool and dim, producing only about 0.17% as much light as our Sun. At Proxima b's orbital distance, It receives about 65 to 70% of the radiation Earth receives, placing it comfortably in the habitable zone. If the planet has the right atmosphere, if it has greenhouse gases to trap heat, liquid water could exist on its surface. The discovery was front-page news around the world. The closest star to the Sun had a potentially habitable planet. It immediately became the subject of intense scientific interest and public fascination. Books were written about it, science fiction stories imagined civilizations living beneath Proxima's red glow, and serious scientists began planning how we might study it or even reach it. But being in the habitable zone is just the first step. Does Proxima b actually have an atmosphere? The question is critical because without an atmosphere, the planet would be a barren, airless rock. Its water, if it ever had any, long since lost to space. And there are good reasons to worry about atmospheric retention around a red dwarf. Red dwarfs, especially young ones, are highly active. They produce powerful flares, sudden brightenings where the star's output can increase dramatically in just minutes. They emit high levels of ultraviolet and X-ray radiation. They have powerful stellar winds, streams of charged particles flowing out from the star. All of this bombardment can strip away a planet's atmosphere over time, particularly for planets in close orbits like Proxima b. A study published in 2017 by Catherine Garcia Sage and colleagues at NASA's Goddard Space Flight Center modeled what would happen if Earth were in Proxima b's position. They found that the intense stellar radiation could strip away an Earth-like atmosphere up to 10,000 times faster than solar wind strips Earth's atmosphere. Even accounting for the planet's potentially stronger magnetic field, which could offer some protection, the results suggested that maintaining an atmosphere around Proxima Centauri b would be challenging. This doesn't necessarily mean Proxima b is airless. The planet might have started with a much thicker atmosphere that's been slowly eroding but hasn't been completely stripped yet. It might have geological activity, volcanism driven by tidal heating from its eccentric orbit that's constantly replenishing atmospheric gases. It might have a very strong magnetic field that protects it more effectively than models suggest. We simply don't know. Unfortunately, Proxima b doesn't transit its star from our perspective. This means we can't use the transit method to study its atmosphere. We can't watch starlight filtering through the planet's air, revealing the chemicals present through their absorption spectra. All we can do is model, predict, and wait for technology to advance enough that we can study the planet directly. Some observations have been attempted. Astronomers have searched for radio emissions that might indicate a magnetic field. They've looked for reflected light that might tell us about the planet's surface or atmosphere. So far, results have been inconclusive. The planet is there, we know it exists, but characterizing it remains maddeningly difficult. Yet Proxima b's closeness makes it unique. At just over 4 light-years away, it's close enough that we can realistically think about sending probes there within a century or two, using technologies we're already beginning to develop. The Breakthrough Starshot Initiative, announced in 2016 by Yuri Milner, Stephen Hawking, and Mark Zuckerberg, proposes doing exactly that. The concept is to build thousands of tiny spacecraft, each weighing just a few grams, equipped with light sails. These starships would be accelerated by powerful lasers on Earth, pushing against their sails with beams of light, accelerating them to about 20% the speed of light. At that velocity, the journey to Proxima Centauri would take about 20 years, with data transmission back to Earth taking another 4 years. It's an ambitious, almost science-fictional plan, but the underlying physics is sound. The engineering challenges are enormous, from building lasers powerful enough to accelerate the probes to developing electronics that can survive the journey and function decades later in an alien solar system. But it's not impossible. It's the kind of project that, with sufficient funding and international cooperation, humanity could accomplish within our lifetimes. Imagine receiving the first images from another star system, the first direct observations of Proxima Centauri b. Imagine finding out if it has an atmosphere, if it has oceans, if its surface shows any signs of geological activity, or, dare we hope, biological activity. It would be one of the defining moments in human history. Proof that we can reach beyond our solar system, that other worlds are not forever beyond our grasp. But even without sending probes, future telescopes will continue to study Proxima b. The planned extremely large telescope, currently under construction in Chile, will have a 39-meter mirror dwarfing Webb's 6.5 meters. It might be capable of directly imaging Proxima b, separating its faint light from the star's glare. NASA's Habitable Worlds Observatory, planned for launch in the 2040s, is being designed specifically to image and characterize Earth-like exoplanets. And Proxima b would be a prime target. These future observations might reveal whether Proxima b has an atmosphere, and if so, what it's made of. They might detect biosignatures or technosignatures, signs not just of life, but of civilization. And Proxima b isn't alone in the Proxima Centauri system. In 2020, astronomers announced the detection of a candidate planet even closer to the star, Proxima d, and hints of possibly another planet further out, though this one remains unconfirmed. The Proxima Centauri system, our nearest stellar neighbor, might host multiple worlds. One or more of them might be habitable, and unlike K218b or TRAPPIST-1, unlike systems hundreds or thousands of light years away, Proxima Centauri is close enough that we might actually reach it, might touch its worlds, and answer directly the questions we can only probe from afar for more distant systems. Proxima Centauri b represents both the promise and the frustration of exoplanet science. It's so close, cosmically speaking, right next door. Yet, even being next door, it remains mysterious, studied indirectly, understood incompletely. It reminds us that for all our technological prowess, for all our sophisticated telescopes and clever detection methods, the universe is vast, and its secrets are not easily surrendered. But what if, on one of these worlds, whether K218b or Proxima b, or another planet we haven't yet discovered, there's not just life, but intelligent life? What if we're looking for biosignatures when we should be looking for technosignatures? Signs not of microbes or plants, but of civilizations. The meaning of occupied. When we talk about finding Earth 3.0, about discovering a planet that might be occupied, the word occupied can mean many different things. It could mean a world covered in microbial mats and simple algae, an ocean teeming with microscopic life, a planet in the early stages of its biological story. It could mean a world with complex life, forests and creatures, ecosystems as rich and varied as those on Earth. Or it could mean a world with intelligent life, civilizations, technology, beings who look up at their own night sky and wonder, as we do, whether they're alone. The search for biosignatures focuses on that first category, signs of life at any level. We look for gases that shouldn't be in a planet's atmosphere in significant quantities unless life is continuously producing them. Oxygen is the classic example. Earth's atmosphere is about 21% oxygen by volume. Without life constantly producing it through photosynthesis, that oxygen would react with rocks and minerals, combining with iron and other elements, disappearing from the air within a few million years. The presence of abundant oxygen, especially in combination with other gases like methane that shouldn't coexist at equilibrium, is considered a strong biosignature. Methane and oxygen react with each other, so if you find both in significant quantities, something must be continuously replenishing them. On Earth, that something is life. Photosynthetic organisms producing oxygen, and methanogenic bacteria, termites, cattle, and other organisms producing methane. Other potential biosignatures include phosphine, a gas that on rocky planets appears to be produced almost exclusively by biological processes. On Earth, anaerobic bacteria create phosphine, though in very small quantities. The controversial detection of phosphine in Venus's atmosphere in 2020 sparked intense debate about whether it could indicate microbial life in the planet's clouds, though subsequent studies have raised doubts about whether phosphine is actually present. Dimethyl sulfide, that molecule tentatively detected on K2-18b, is another strong biosignature candidate. On Earth, it's created primarily by marine phytoplankton, as they break down dimethyl sulfoniopropiant, a compound they use to regulate their internal salt concentration. The fact that we don't know of any abiotic process that produces DMS in significant quantities makes it a particularly exciting molecule to search for. Though again, our knowledge of what's possible on worlds very different from Earth is limited. But biosignatures come with a fundamental challenge: false positives. We need to be very careful to distinguish between gases produced by life and gases produced by geological or chemical processes that have nothing to do with biology. Oxygen, for example, can be produced without life through photolysis, the breakdown of water molecules by ultraviolet light. If a planet lost its ocean to space, with the hydrogen escaping and the oxygen left behind, it could have an oxygen-rich atmosphere with no life at all. This is why context matters so much. Detecting a single gas isn't enough. We need to understand the planet's environment, its star's radiation output, its geological activity, the ensemble of molecules in its atmosphere. A true biosignature is most convincing when it's a pattern of chemicals that don't make sense together unless life is present, when the planet's state is out of thermodynamic equilibrium in a way that requires constant energy input, like life provides. Technosignatures, signs of technology, offer a different approach. Instead of looking for the chemical byproducts of biology, we look for signs of intelligence, of civilization, of technology that might produce detectable effects. The search for extraterrestrial intelligence, SETI, has been doing this for decades, primarily by searching for radio signals of artificial origin. The classic idea is that an advanced civilization might broadcast radio signals either deliberately to announce their presence or as leakage from their own communications and radar systems. Earth has been inadvertently broadcasting radio signals into space since we developed radio technology, a growing sphere of electromagnetic radiation now extending about 100 light-years from Earth, carrying reruns of old television shows and the pings of military radar systems. But Radio SETI has faced challenges. The universe is vast, and we don't know where or when to listen. Radio signals spread out and weaken with distance. A civilization's radio loud phase might be brief, perhaps just a few centuries, as they develop radio technology, and then move on to more efficient communication methods like fiber optics that don't leak into space. And we've been listening with increasing sensitivity for over 60 years without any confirmed detection of alien signals. This lack of detection doesn't mean there's no one out there. It might just mean they're rare or far away or not broadcasting in ways or at frequencies we're monitoring. The Fermi paradox. The apparent contradiction between the high probability of extraterrestrial civilizations existing and our lack of evidence for them has spawned countless proposed explanations. From the idea that we're alone to the suggestion that advanced civilizations deliberately avoid contact. Modern SETI has expanded beyond radio. Optical SETI looks for laser pulses, brief flashes of light that might be used for interstellar communication. Laser signals can be extremely powerful and tightly focused, making them potentially detectable across vast distances. Searches for megastructures, enormous artificial constructs like Dyson spheres that an advanced civilization might build to harness their star's energy, look for unusual patterns in stellar light that might indicate artificial structures. Atmospheric technosignatures are a particularly intriguing new frontier. Just as our own atmosphere bears the chemical fingerprints of human industrial activity, an alien civilization's atmosphere might show signs of their technology. Chlorofluorocarbons, or CFCs, the chemicals that depleted Earth's ozone layer, are entirely artificial on our planet. If we detected CFCs in an exoplanet's atmosphere, it would be hard to explain without invoking technology. Nitrogen dioxide, a pollutant from combustion, is another potential technosignature. While it can be produced naturally, particularly by lightning, very high concentrations might indicate industrial activity. A civilization that hasn't transitioned to clean energy might have an atmosphere laden with the byproducts of their technology, detectable from light years away. A recent study led by Sophia Sheikh at the SETI Institute asked a simple but profound question. If an alien civilization had technology similar to ours, from how far away could they detect Earth? The answer depended on what they were looking for. Earth's most detectable technosignature is currently our radio emissions, particularly high-power radar systems, potentially detectable from up to 12,000 light-years away. Atmospheric technosignatures like nitrogen dioxide pollution have become more detectable thanks to advances in instruments like JWST. Though they're still challenging to detect from interstellar distances, the study was a sobering reminder of how much our detectability has changed over time. A century ago, Earth would have been almost invisible to distant observers. Today, we're broadcasting our presence, though faintly, across thousands of light years. In another century, if we transition to cleaner technologies and more efficient communications, we might become quieter again, harder to detect. This temporal aspect is crucial. Civilizations might only be detectable for a brief window of their development, that period when they're technologically advanced enough to produce detectable signals but haven't yet advanced beyond the need for such signals. If this window is just a few centuries and civilizations are spread across billions of years of potential development time, the chances of two civilizations being simultaneously detectable to each other drop dramatically. But what if we did detect a technosignature? What if JWST or a future telescope found unambiguous signs of industrial chemicals in an exoplanet's atmosphere? Or if SETI detected a radio signal that could only be artificial? It would be, without exaggeration, the most important discovery in human history. It would answer the ancient question, we are not alone. The implications would be staggering. Every field of human endeavor would be affected. Philosophy and religion would grapple with the reality of other intelligences. Science would have a new field of study, comparative civilizations, learning from how another species developed technology and science. Politics and international relations would be forced to think in terms of humanity as a single entity in a larger cosmic community. Even finding just microbial life, simple bacteria, or their alien equivalent, would be revolutionary. It would prove that life isn't a unique accident, that the chemistry that led to biology on Earth can happen elsewhere. It would validate astrobiology as a field and transform our understanding of life's place in the cosmos. Finding two independent origins of life in one galaxy would suggest that life is common, that the universe might be teeming with it, even if intelligence is rare. This is what makes the current era so exciting. We're not just speculating anymore. We're actively searching with tools powerful enough to potentially find answers. JWST is characterizing the atmospheres of habitable zone planets. SETI continues to scan the skies with ever-improving sensitivity. Future telescopes will have even greater capabilities. Within our lifetimes, we might transition from wondering if life exists elsewhere to knowing whether it does. The question of whether a planet is occupied encompasses this entire spectrum, from simple microbes to advanced civilizations. As we study worlds like K2, 18b, and Proxima Centauri b, as we search the atmospheres of exoplanets for telltale chemicals and scan the sky for artificial signals, we're engaged in the most profound scientific endeavor humanity has ever undertaken. The search for our place in the cosmic story. The quest to understand whether we're alone or part of a larger community of living, thinking beings. The implications for humanity. Imagine, for a moment, that the signal from K2, 18b is confirmed. Imagine that additional observations push the dimethyl sulfide detection to 5 sigma significance. That follow-up studies rule out all plausible abiotic explanations. That the scientific consensus builds toward the conclusion that, yes, we've detected signs of life on another world. How would that change us? How would it alter the human story? The most immediate impact would be on science. Astrobiology, the study of life in the universe, would transform overnight from a largely theoretical field to one with actual data. We'd have 2 independent examples of life, Earth and K2, 18b, and even with just 2 examples, we could begin to ask questions about what's universal and what's contingent about biology. Does life elsewhere use the same genetic system we do, DNA and RNA, or something entirely different? Does it use the same 20 amino acids or different ones? Is it carbon-based like Earth life, or could it use different chemistry entirely? Does it require liquid water, or could life exist in liquid methane or ammonia, or something more exotic? These questions, which we can currently only speculate about, would become empirical questions, addressable through observation and experiment. The discovery would also reframe the Fermi paradox. If microbial life is common enough that we can find it on a planet just 124 light-years away, then life is probably abundant in the galaxy. But the paradox remains. Where are all the civilizations? The gap between simple life and intelligence might be vast. The evolutionary path from bacteria to technological civilization so difficult and unlikely that even in a galaxy where microbial life is common, intelligence remains rare. This relates to the concept of the Great Filter, a hypothetical barrier that prevents civilizations from becoming widespread and long-lasting in the galaxy. The filter could be in our past, something like the origin of life or the evolution of complex cells, a step so unlikely that most planets never take it. If that's the case, then finding any life at all would be rare. But once it exists, progressing to intelligence might be relatively likely. Alternative, the filter could be in our future, some challenge that technological civilizations typically fail to overcome. Nuclear war, environmental collapse, artificial intelligence gone wrong, or something we can't even imagine yet. If simple life is common, but we never find evidence of civilizations, it would suggest the filter lies ahead of us, a sobering thought that should inspire us to navigate our own challenges more carefully. Finding life would also have profound philosophical and religious implications. Many religious traditions have focused on humanity's unique place in creation, Earth as the center of God's attention, humans as the special creation. Learning that life exists elsewhere, that we're not alone, would require reinterpreting these traditions. Some theologians have already begun this work, arguing that the existence of extraterrestrial life is compatible with most religious worldviews, that a creator capable of making one world inhabited is certainly capable of making many. For secular philosophy, the discovery would be equally significant. It would validate the Copernican principle, the idea that there's nothing special about our position in the universe, that Earth is just one planet among countless others. It would remind us of our cosmic context, our place as one species on one world in a vast universe, and perhaps it would inspire a sense of responsibility to preserve and protect the life we have here. The psychological impact might be subtle but profound. Humans have a tendency toward parochialism, seeing our own concerns as central and all-important. Learning that life exists elsewhere might broaden our perspective, help us see our local problems in a larger context. It might inspire a sense of unity, the idea that all life on Earth, all of humanity, despite our differences, is part of the same story, the same chapter in a larger cosmic narrative. Or it might have the opposite effect. Some worry that discovering we're not alone could lead to existential anxiety, a sense of insignificance, or vulnerability. If life is common, if intelligence has evolved elsewhere, does that diminish us? Does it make our achievements, our art and science and philosophy, less special? These are questions without clear answers, and the response would likely vary from person to person, culture to culture. Some would feel wonder and excitement, a sense that the universe is even more magnificent than they imagined. Others might feel fear or uncertainty. The discovery would be processed through the lens of each individual's worldview, each society's values and beliefs. For the scientific community and space agencies, finding life would reshape priorities. Missions to study K218b or other biosphere-bearing worlds would become paramount. New telescopes would be designed and built specifically to characterize these planets in detail. International cooperation in space exploration might increase as the global community recognizes the importance of this shared endeavor. There would also be practical questions. How do we communicate? Even if we're just detecting biosignatures from microbes, not technosignatures from civilizations, the question of potential future contact arises. Should we try to send messages? Should we announce our presence? Or observe quietly? Different factions would argue different positions, and there's currently no international framework for making these decisions. If we ever detected a technosignature, an unambiguous sign of intelligence rather than just life, the implications would be even more profound. We'd know there are other thinking beings out there, other civilizations wrestling with the same kinds of questions we face, even if they're thousands of light years away, making two-way communication impossible on human timescales. Just knowing they exist would change us. We might learn from them, studying their technology or their solutions to problems we face. We might find common ground in mathematics or physics, universal languages of logic and natural law. Or we might discover that intelligence can be so different from our own that meaningful communication is impossible, that other minds work in ways we can't comprehend. But perhaps the most important implication is simpler. Finding life, whether microbial or intelligent, would be a moment of profound unity for humanity. It would be a discovery we made together, a truth we learned as a species. In a world often divided by nationality, religion, ideology, and countless other differences, the discovery of extraterrestrial life might remind us of what we share: our home planet, our biology, our common origin in the long story of evolution on Earth. We are, all of us, Earthlings. Every human who has ever lived, every creature that crawls or flies or swims, every plant and microbe shares a common ancestry, a single origin in the early history of our planet. We are one family of life, related through deep time. Finding life elsewhere would highlight that unity, remind us that for all our differences, we're all part of Earth's biosphere, all products of this one world's 4 billion year experiment with biology. And maybe that perspective, that sense of shared identity and common fate, is something we need right now. As we face challenges that transcend national borders, climate change, and environmental degradation, and the sustainable use of our planet's resources, perhaps a cosmic perspective could help. Perhaps knowing we're not alone, that life is precious and rare in the universe, even if it exists elsewhere, might inspire us to take better care of the life we have here. The search for inhabited worlds is, in a sense, a search for ourselves. We're trying to understand our place in the cosmos, to know if we're unique or part of a larger community. And in that search, in that reaching outward to the stars, we might find not just answers about what's out there, but clarity about who we are, what we value, and what kind of future we want to build. Conclusion. As you lie there, perhaps feeling sleep beginning to pull at the edges of your consciousness, let your thoughts drift through the cosmic vistas we've explored together. Think about those 7 worlds of T-R-A-P, P-I-S-T, one, each one bathed in the red glow of their dwarf star, possibly harboring atmospheres, perhaps sheltering life in forms we've never imagined. Think about K2, 18b, with its deep oceans beneath a hydrogen sky, where tentative signals suggest something might be producing molecules we associate with life. Think about Proxima Centauri b, our nearest exoplanetary neighbor, close enough that we can dream of reaching it, of touching another world that orbits another star. These aren't science fiction. These are real places, real worlds orbiting real stars, places you could point to in the night sky if you knew where to look. And we're studying them now in your lifetime, using tools like the James Webb Space Telescope to peer into their atmospheres, to search for signs that might indicate life. We're living through a revolution in human knowledge, a transformation in our understanding of our place in the cosmos. Within the next few years, maybe within the next few months, we might have an answer to one of humanity's oldest questions. We might find definitive evidence that life exists beyond Earth, or we might discover that while life is rare, we're not alone in facing the challenges of existence on a rocky world around a distant star. Either way, the search continues, driven by our insatiable curiosity, our need to understand the universe we inhabit. The James Webb Space Telescope is out there right now, nearly 1 million miles from Earth, its golden mirror reflecting starlight from across the universe. Every moment, it's collecting photons that have traveled for years or millennia, or billions of years to reach it. Some of those photons pass through the atmospheres of distant worlds, carrying information about the chemicals present there, hints about whether those worlds might be occupied. As you drift off to sleep, know that this search is ongoing. Scientists around the world are analyzing Webb's data, planning new observations, building new theories about what we might find. The future holds promise of even more powerful telescopes, even greater discoveries. We're on the cusp of answering questions that humans have wondered about for as long as we've been able to wonder. Sleep well, knowing that the universe is vast and filled with wonders, that our understanding grows with each passing day, and that somewhere out there, perhaps on a world like K2, 18b, or Proxima Centauri b, there might be something looking back. Before you go, if this journey through the cosmos has brought you peace or sparked your curiosity, please take a moment to subscribe to the Science Pillow. Your support allows us to continue creating these explorations, these gentle voyages through the mysteries of science and space. And if you enjoyed this particular journey, hitting the like button helps others find their way to these calming, educational experiences. Thank you for spending this time with me, exploring the universe and the search for life among the stars. Until next time, rest well, dream big, and remember that you're part of this cosmic story, a conscious observer in a universe full of wonders yet to be discovered. Good night.